Imagine we have one proton and one neutron. They're attracted by the nuclear force, which is really, really strong. And when they're separated like this, they actually have nuclear potential energy, believe it or not. That's no different from taking a ball and lifting it off the ground. By separating the ball from the ground, I give it gravitational potential energy. And when I say that these have nuclear potential energy, all that really means is they want to move closer to each other because of the strong attractive force. So what happens if we just let them go? Well, they move in toward each other, and a nucleus is formed. But these nucleons, which are now bound side by side, are no longer separated. They've just lost their initial nuclear potential energy. But wait a second. We know that energy can't actually be lost. It can only be converted into other forms. So what's the energy converted to in this case? Well, we know from experiments that the potential energy is converted into light, or electromagnetic radiation. But as Einstein famously discovered, energy is equivalent to mass. That means if these nucleons emit light, then they've just lost some energy, and because they've just lost some energy, they've lost some mass. So we can look at these nucleons, and because they emit light, they lose a little bit of mass, and I'll represent that by making them smaller. Okay, if you have two nucleons coming together like this, then each one is going to emit roughly 3 mega electron volts. The total energy that had to be lost in order to put together this nucleus, the total amount is 3 for this one, plus 3 for that nucleus, that nucleon, which gives us a total energy of 6 MeV. We call that the binding energy. Binding energy is the energy released when a nucleus is formed. Now, per nucleon, for each of those circles I've shown, the amount of energy lost, the binding energy, when forming the nucleus, is 3. So you might be wondering, does every nucleon always give off 3 mega electron volts? Well, let's start with one more. So now let's start with 3 nucleons instead of 2. We let them go, they move together, they give off light. The light carries away some of the energy, and hence some of the mass. So we can show that these get smaller. They are less massive. Now, in fact, if you start with 3 nucleons instead of 2 nucleons, then each of these is going to give off a little bit more energy, 4 mega electron volts. So the total binding energy, the total energy lost in forming the nucleus, is 4 plus 4 plus 4, which is, 12, not 16. But per nucleon, each of these little circles, the protons and neutrons, each one loses a little bit more energy than the last example. And this trend continues. You start with 4, they come together, they give off light, the light carries away energy and hence also some mass. And each one now, starting with 4, each one gives off roughly 7 mega electron volts. So the binding energy, of course, goes up because there's more nucleons, there's more things giving off energy. But, interestingly, each one gives off more energy than if you had just started with 3 nucleons. So the binding energy per nucleon, the amount that each nucleon gives off, has increased. This trend continues. Whoa! It continues until you get up around 90 nucleons. When you get up to 90 nucleons, and there's not actually 90 here, each one of those nucleons will give off roughly 9 mega electron volts for a total binding energy of 9 times 90, 9 times 90, or 810. And this, believe it or not, is about the peak. The nucleons max out at around 9 mega electron volts per nucleon. If you go up any farther, like up to 100 nucleons, then they actually give off a little less energy. Each nucleon only gives off around 8.7. Of course, the binding energy has gone up because you have more things giving off energy. So the binding energy still increases from the last example. So what do we see? We see that as you go from small nuclei to medium-sized nuclei, the binding energy per nucleon increases. Then as you go from medium nuclei to larger and larger nuclei, the binding energy per nucleon starts to decrease.